So let's plot the top 10. There we go. See, now we have a more accurate set of models, of 10 models compared to this, because we honed down, right? We zoomed in on this range, and we created a new set of, remember this, the range here is -20 to 40, whereas here it's -5 to 20, right? And here it's -5 to 5, and here it's 1 to 3. So we're really zoomed in. We zoomed in on this area. And so these models are far more accurate. But among them, you can see the light blue ones are more accurate, and then dark blue ones are less accurate. So now let's find the best model. And the best model, to find it, we can use a function called optim. So this process, right, it helped us hone down on the closest models, right? So this, for many applications, might be enough for you, right? But the whole intent of this was to show you the manual process of, you keep repeating this until you keep getting a smaller and smaller distance, until you find one where like it doesn't make sense to keep going more, and you use that model. Instead of doing all that manually, you can use a function called optim, which we already pulled up. And this is general purpose optimization. So you supply it with a function and parameters, or starting parameters, and a function to measure distance, and a data set, an actual data set, and it'll actually do this process for you in the background indefinitely until it finds the most accurate set of parameters. So the parameters, the first argument, so optim. So let's start with 0 and 0, okay, for A1 and A2. And the distance function that we're going to be using is distance. And the data is sim1. If you run this, right, you get these two parameters, which are 4.22 for A1 and 2.05 for A2. So if we actually go into our grid, and what we do is we go down to the best model, the smallest distance. We have 4.38 and 2, and these are the actual parameters for the actual best fitted model for these points. And you can see that they're pretty close, right? There's a very minimal error here. There's like 0.05 difference between 2 and this number. And here we also have a very minimal difference. So this shows that our manual process, our iterative process, gives us a pretty accurate approximation of the best model. But this is the actual best model. And then we can actually plot this. Let's do that very quickly. X and Y, geom point. Let's make it 2. And the color, again, let's make it gray, the shade of gray. And then let's plot this perfect, or not perfect, but the closest, the fitted model, basically, which would be best parameter, the first one, right, which is 4.22, and the slope would be 2.05. And if we were to plot this, but we have to spell this correctly, there we go. So this line most accurately describes this data set. This means that if you were to lose this data set, actually we can't do that here, but this basically means that this line can now replace this data set. You can remove this data set now, and you can use this line to approximate this data set. So when you're given inputs, when you're given numbers, and people want to know the output, you can just plug it into this line, and like let's say 5. So you put in 5, and the output is, something like 14.8, right? That's your output. In reality, the output is here and here and here, but the average in general would be around here. So you're predicting a number that's pretty close to the actual Y values. It's not something that's out here or down here. It's actually very accurate. So this is what essentially machine learning is. You're creating a model that best describes your data set, so that when you remove your data set and you put in new numbers, new inputs, you can somewhat accurately, as accurately as possible, predict the output values. So this will be the best model. So don't worry, we're not going to be doing all of this for every single model. This is just for you to get an understanding of what's going on in the background. But we're going to basically be outsourcing a lot of this work to the Tidy Models set of packages, and that are going to make a lot of things easier for us. But before we do that, let's look at how we would do this in the base R. So base R actually comes with functions to do this, right out of the box. So let's create, and for linear regression, it's a function called LM. So in base R, LM lets you fit linear model. So it does all of this work and does everything in the background. All you do is you have to supply it, you have to let it know the relationship of the variables. So the outcome variable is Y and the input variables are just X, and the data is sim1. So let's just create something like this, just so you know that we finished this manual part. Now we're trying to fit a model on our data set using a built-in function instead of doing everything manually on our own. So let's run this, and there we go. We have the result. We can look at the coefficients like so, and look, we get the same results. Same, not exactly the same, right? Because our measuring, the way we measure the distance might be slightly different from the way they measure it, but it's pretty accurate. It's 4.22, 4.22, 2.05, 2.05. So instead of all the work we just did here, right, all you had to do was just to run this line of code. And that's the beauty of R, right? It just lets you to fit models and build models right out of the box without any work, right? This is essentially the summary of what we've been doing for the past half an hour. And then we can use a package called Broom, which helps us tidy up the results of our machine learning functions, because each model has a different function in R, and they might have different ways of displaying their output. So what Broom does is it helps you tidy up all of them into one centralized format. So if we run this, you see all the outputs. So the standard error between this model's prediction and the actual Y, and different statistics that we're not going to go into because this requires a lot of statistics and probability and mathematical knowledge. And the p-value we'll cover in the next section. But essentially, the p-value is very small. That means that the model is pretty accurate. So the p-value is a way of assessing the accuracy of a model. We're going to cover all of that in the next section. But this is basically how you would do all of what we just did in base R. What we did it all from scratch manually, but this is the official way to do it in R. So we're able to find our model. That's our model that describes this line, that describes our data set. So let's very quickly now do some predictions. So we have our model. How do you predict on new data? So let's load our sample from the previous, if you guys remember. We don't have it, so install .packages, our sample. So we're loading our sample, installing it, and if you remember, this is how we split our data into a training and testing data set. We did this in the data preprocessing section of this course. If you don't remember, go back and review that. But essentially, we did all of this, we found our model. Now we have to use it practically. Like, what's the point of all of this, right? We want to use it to predict on real data. So let's load our sample. Let's split our data. These are the steps you would actually be taking. This was all done for teaching purposes, education purposes. But what you would actually do is you would take your data and you would create a testing and training data split. So we're splitting our data, and we want to create a training data set, and we want to create a testing data set. Okay, so now we've split our data set into training and testing data. Where did that go? We haven't run it. There we go. Testing. So we have 2 data sets now. So the problem with doing this right away with all their data is you have no way of validating the accuracy of your data set, because remember, we don't want to overfit the data. We don't want the model to overfit to our data and then have poor performance when it comes to new data. So that's why we create the initial training and testing data split, and then we do the training on the training data only. So let's create our model, linear model. We define our outcome variable to be y, the input to be x, and the data to be data train. Okay. And let's run that. So we have our prediction. Let's just call it, let's do this, or actually let's do this very quickly. So these are the steps you should follow when training any model. So we do a training testing split, and then here we train our model, or we fit our model. So we find the best fitting model, right? And let's do that. And then we have our prediction. And here our prediction would be, we want to predict using our model here. This is a function, again, a built-in function. We put in the model, the result, right? The result of our fitting. So this is our fitted model. And we want to predict on our test data set. And if we run this, these are the predictions. And data test, if you were to run this, these are the actual values of y here. So you can see that our prediction is like 10.4, but the actual is 10.5. That's pretty close. Our prediction here is 12.5. This is 11.9. Again, pretty close, and so on and so forth. And just to make it easier for us to see this, let's actually put this as a column into the test data set. So prediction, let's make a column called prediction. There we go. Let's save this into our data set. So now if we run data test, see, these are our prediction. This is the actual y value, and this is the prediction based on the model that we found here. And remember, the model you can view like so. So based on this model, these are the predictions, and these are the actual values. So you can see how close they actually are. But like, this is pretty far, right? This is not too accurate, but comparatively, like the other ones are pretty accurate. So in general, this is a very, a pretty good model. But we want to make sure it's not overfitted or underfitted to our training data. So that's why we have the testing data set. And so let's go ahead and plot and see these two compared. So let's plot the prediction, and let's make the size of that 3 and the color red. So this will be our prediction, in the prediction of the model that we generated, and we want to see how accurate it is, right? And then let's plot the actual y values as points, and we'll make the size of that 5. We'll make the color of them green, and alpha, we'll just make it 3/4. And then we can, let's do this. There we go. So what we basically did here is the green points, they represent the test data set, okay? And the green ones are the actual values for the test data set, the actual y values. And the red is our model's predictions, okay? And then you can see that original training data set as so. So this was the training data set that was used to find this line. This line is a prediction of what the actual values of green are. So you can see that red is a pretty close approximation to the green points. And this is all the test data set. So, this is pretty cool. And then we can measure the accuracy, because you always want to be able to measure a numeric accuracy. So this is visually, we can see that they're pretty close. And for that, we use a tidy models. By the way, Broom is a package from the tidy models universe, which is a subset of the tidyverse universe. Yardstick is also another model. We're going to be going over these in more detail in the future videos. But there's a metrics function within Yardstick, and I think I have to install Yardstick. And there's a metrics function which will give you the accuracy of a model like this. So let's just let that load, and here, the test data, and we can actually, Yardstick metrics. The first argument would be the data and then the true values of it. So data and the Y column. So you have to supply a data set like the one here, which has the true and the predicted values within the data set. So we have Y and we have pred. So we give it the data set, and then Y are the accurate, the true values. And then we have the estimate, which is the prediction column, pred. And if we run this, we can find, so RMSE, that's what we were doing, right? Root mean squared error. And then there are other like mean average error, like there are different metrics, but it gives you all of it. And it gives you like the error rates of it. So you can see that the errors are pretty low. This means that this is a pretty accurate approximation for our model. And we did that by validating it using a test data set. So we proved that there's no overfitting, that this is a good representation of the data set, because we withheld the test data set, right? So this model did not see the test data set at all. It just trained on the training data set. So the test data set is a very good measurement of the accuracy of this model. So I know that was a lot of material to cover and a lot of things to digest. What I would suggest is to let this sink in, maybe rewatch this video and maybe redo some of this on your own so that you can really understand each of these steps. I don't want you moving on until you understand why we did everything we did here. And that's going to really help you, because if you really understand this video, you're going to have a very good understanding of what machine learning is, right? Because then everything in the future, like in the next videos, is just how to optimize the way we do this, how to do this using frameworks and libraries, how to do this on real data sets, how to do this using different algorithms. But it's all the same process that we learned here. And here is where we really like broke it down into manual steps and like saw how everything works. So I would advise you to just review this video and just focus on this video and recreating everything we did in this video. And you can also go to the R4DS book and to the chapter I mentioned in the last video to also read through that chapter and just really make sure you understand what's going on, okay? And understand why we withheld the test data set, how we measure the accuracy, how this represents a model, creating a family of models. So this function is basically doing everything we did in the beginning of the video, creating the family of models, picking the best ones, look at the parameters, optimizing, zooming in, all that kind of stuff in the background, right? That's my suggestion for you. I will see you in the next videos.